Hello and welcome to Module 1, the first component of the 452 course, History and Value of Systems Engineering. This is the portion of the show where we will explain why systems engineering exists today and the function it serves across the business and community. First of all, if you haven't done so already, please read through the concepts of systems engineering as practiced by the Wright brothers, the case study provided. Back in the 1900s, in the very early part of that century, the Wright brothers used these concepts in the development of manned flight. They were by no means the only people trying to develop manned flight, and in fact there were many competitors. At the same time, they weren't necessarily the best aviators or engineers at the time. However, what they did where others did not is they understood the interlinkings of all different systems all throughout the development process with their goal of trying to create manned flight. Because of this, they were able to manage to it and be much more quick to market, and they were the first to be able to accomplish it. While the term systems engineering was first used at the Bell Labs in the 1920s, the concepts have actually been used for much longer than that. The Wright brothers are one example, but if you look at historic texts, even the Bible, Noah specified and gave very clear expectations for this ark must be this tall, this wide, have a door here, and that sort of thing. These are examples of requirements that were designed up front and decided up front, and then the system, which was the ark, had to be able to conform to. Concepts we will hit on coming up. First of all, the operational concept was how the system will be used once in operation. System boundaries, scope, systems, how far they will extend, how many subsystems do they extend to, and where do they not extend to. Requirements, again, what is the system supposed to be able to do? And along with that, the management of requirements. Requirements are very dynamic and need to be modified and managed as the system progresses. A lot of times this is because new information is developed. Either new requirements or requirements aren't as critical as possible, or trade-offs have to be made. Functional analysis, these are the necessary functions to make the system work, typically emerging from the need to meet requirements. Then we get into physical architecture and interface and trade-off decisions. Consider the concept of triple constraints, which is a fundamental component of project management. Triple constraints being time, cost, and scope. Usually you can, if you're not going to meet your project goal or it's in jeopardy, you can crash resources by adding cost, or you can add time to the project, or you can reduce the scope, or a combination therein. Systems engineering is very frequently all about trade-offs, because some systems may be more suboptimal than others, or may have requirements that exceed the needs of others, and you have to look at the system as a whole, not necessarily the individual components. Prototyping, development, and testing. Again, piloting prior to a full launch whenever possible, and then test design and or team activities, which are also demonstrated in this paper. So the first manned flights, you go back even further in history, is late 1700s, early 1800s, all the way up to powered flight in the early 1900s. That's quite a gap if you consider it, from when you go from 20 years to almost 100 years for the next stage. Obviously, since we developed powered flight, we've grown many leaps and bounds in much shorter development cycle. In those developments, you'll see many concepts of systems engineering that have been used. So the system boundary, so for the pilot of the system, that was a fundamental component that the Wright brothers had to incorporate, because previous unmanned flights didn't have a pilot to account for. Now they needed to consider the needs of the pilot, not just what the pilot brings to the table and being able to steer and make decisions, but also fit, form of use, ability to get the information that he or she needs while they are flying the plane, and also be able to control and have all the ability to make decisions and keep the flight lift. Derived requirements, necessary horsepower, thrust of propellers. The Wright brothers looked and said, mechanically, how much horsepower does this flight need to be able to provide in order to get off the ground? How much thrust is needed? And they said these are the requirements that the system has to be able to provide. So when they could design the subcomponents, they could consider those inner workings in there, saying all these have to work together in order to get these the horsepower that we need. If we do not get those requirements, then we need to go back and figure out how do we get over that hump. And then functional analysis. understood the functions of the airplane. This particular drove the design process. So they looked at the functions of, for example, the propulsion system, lift system, stability control system. They considered all those things and actually took a very top-down design system to say from starting point, what are those requirements, what are those fundamental components, and then they designed their flight. This is very contrary to what other approaches had been used up until this time. Most of the time, people would go and say, well, let's just go create a simulation or a pilot of something and just try it. Let's create a mock-up and see if it flies. Whereas instead, the Wright brothers looked and says, what does the system need to be able to do? What are all the components built in there? And they flowed through the systems engineering thought process, which arrived them quicker to market than anybody else. Other systems engineering concepts used included prototypes and testing. So they built successively more complex gliders before building the airplane. Rather than jumping to say, let's go create the airplane right off the bat, how do we create a simple module? What do we learn from it? And then use that to incorporate the next stages in there. They employed sophisticated testing at each level. This, again, was very important to understand. Their end goal was to have a completed system, and that meant build the subsystems out that supported that system. Trade-off decisions. You look at the requirements up front, and they said, well, we need this amount of propulsion in order to get off the ground. They also looked and said, well, on top of that, if we get that much in there, but we have to add weight to the airplane, that won't get us where we need to go because now we need more propulsion. So they had to look and say, how do we control that and how do we minimize that? At the same time, if you add more propulsion and more weight and meet that component, now you're potentially losing control because the ability to steer and navigate a bigger plane is more dangerous or is more difficult. So they considered the concepts of these trade-off decisions as they were developing the system. Testing of the system. They did extensive testing even during gliding test. They created a wind tunnel to address specific needs, and they were very careful about selecting their test site. They wanted something that is truly representative. This is another failed component of many systems in today's world where people want to simulate what is not necessarily winding up to be your end test result or test environment. In some cases, this is fairly difficult to do. For example, if you're sending a space shuttle up to outer space, it's difficult to simulate the effects of outer space unless you actually go up and do that. However, as much as you can simulate the concepts of, well, the cold, the vacuum, weather, all those things that impact that, that's how you want to simulate because that will impact whether or not your final product or final system works as you're hoping to do. So, why is systems engineering important? Well, the reality is this is becoming a bigger deal in business as organizations and systems get increasingly complex. So consider the complexity of a computer or a computer chip. Years ago, a simple calculator was as complicated as technology as you get. It's said now the smartphones that we have in our pocket have more technology at our fingertips than we had when we originally sent a shuttle to the moon. You look at the rate of change, and that's going to continue to increase, and there's going to be even more subcomponents and more needs to manage things from a global and a systems perspective. So systems engineering's response to these challenges is to look at things as a whole. Rather than look at each individual subsystem, which is often done in an organization, try to step back and look and see how everything links together and not worry about success at an individual level unless it translates to success as the overall whole. Competitive marketplace for providing a faster delivery, ordering a product online. Nowadays people want it in 24 hours. Years ago it used to be a week is perfectly fine, and before that they may not have even had those expectations. Those systems are becoming increasingly complex and needed to manage today's business and consumer needs. Focus on providing a balanced system solution, focus on managing risks, and leadership in a distributed and integrated development environment. Sub-leaders typically are responsible for their own individual area, and while some people have a more global view, even they still typically look and say, well, I'm going to be judged based on the success of my individual component. Systems engineers are a needed component of management or leadership to be able to see the whole and to make those decisions at a more global level. That means that if a subsystem is meeting its goal already, it still may not be sufficient. whereas another subsystem that is not meeting its goal may be sufficient with the current level of performance. Also, if one is meeting its goal, it might make sense for them to have a trade-off where they are meeting lower performance in order to make another area more successful. This is often difficult for somebody to do in a vacuum. However, if you're looking at it from a global structure and presenting that to your executive leadership or organizational leadership and make a good solid case for it, that's the fundamental nature of the systems engineering role.